All right, welcome to my presentation, which is about a model of individual differences in gaze control during reading. This is joint work with Sebastian, Arzt, Tobias, Scheffer, and Reinhold Kliegl, all from the University of Potsdam in Germany. So the general topic of this talk will be statistical models of eye movements during reading. So when we are reading a text, we kind of fixate and visually recognize individual words, while at the same time lexically and semantically processing the actual text content. And this is a pretty complex process that kind of relates visual, oculomotor, and cognitive aspects. And correspondingly, the eye movement patterns that we get out of this process are also relatively complex, in the sense that our eyes don't just smoothly move through the text, but rather, for example, certain words are skipped or other words are maybe fixated multiple times, and there are also sometimes regressions to an earlier position in the text, depending on this kind of interaction between cognitive processing of the text and oculomotor control and visual recognition of words. So overall, the eye movement patterns that we see provide us with a relatively detailed record of these visual, oculomotor, and linguistic processes that go on during reading. And because eye movements represent these specific visual and lexical processes, they tend to be highly characteristic for individual readers. So if you look at different readers, different individuals, then typically you will see significant differences in observed eye movement patterns. And in our work, we basically studied statistical models of such eye movement patterns that are focused on representing these individual differences. And the key result of our work is that we show that using such models, we can actually infer the identity of a reader from the observed eye movement patterns with very high accuracy. So we can actually kind of recognize people by the way they move their eyes during reading, because these eye movement patterns kind of reflect individual cognitive and visual and motoric processes in the brain. And this might have certain applications in the area of biometry, for example, like validating access to documents. So you could imagine that if someone is reading a classified document and we are actually able to kind of observe the eye movements of the reader, then we could check if this person is indeed authorized to view that particular document or something like that. Okay, so that was a brief motivation. Here's an outline for the rest of my talk. So I'll first go into a bit more detail about the problem setting and say a bit about the data that we have. I will then present the statistical model of eye movement control during reading that is focused on representing these reader-specific differences. And finally, I'll present an empirical study that shows how eye movements can be used as a biometric feature to identify readers from their eye movements. Okay, so here's a slightly more formal problem setting for this biometric task. So at training time, we would be given a set of readers. This is the different individuals that we'd like to distinguish. We are also given a set of text X, which consists of individual documents or phrases X1 to Xn. And then for each pair of a reader and a text, we assume that we have eye movement observations SIR. So SIR are the eye movements of reader R on the text XI. And we assume that these SIR are kind of sampled from reader-specific distributions over eye movements given a text. So we assume that there are differences between individual eye movements, and therefore these SIR are kind of sampled from distribution P of S given XI and the specific reader R. And then at application time, at test time, we're going to observe a novel arbitrary set of text X bar. And these text X don't need to be in any way related to the training text. So we don't need to observe the eye movements on the same text that we've seen in the training data. This can be any novel text. And we observe corresponding eye movement patterns S bar generated by an unknown reader on this novel text. And basically what we want to do is infer the most likely reader to have generated these novel eye movement patterns, okay? So that's a kind of biometric problem setting where we want to identify readers from the eye movements. Okay, so I have one slide about the kind of data to get you give you a feeling of what the data looks like. So generally, we can nowadays record eye movements with relatively high spatial and temporal resolution using modern eye tracking technology. And essentially, these eye movements consist of sequences of so-called saccades. Saccades are kind of short ballistic movements from fixation position to fixation position. And the data that you get out of an eye tracker is basically the positions in the text that have been fixated, so people have been looking at, with an average distance between positions of about 7 characters in typical text reading. And you get the fixation durations, so for how long a certain position in the text was fixated by a reader. And that's an average 200 milliseconds in typical text reading. But this is also depends a lot on the individual. Okay, so that was the problem setting and the data. I'm now going to describe the statistical model of eye movement control that we use to distinguish reader or to kind of fit reader-specific distributions to the data. So as I said, the goal at test time is to predict the most likely reader to have generated some novel eye movement patterns that we observe at application time. And we're going to solve that problem by essentially estimating reader-specific generative models of the form P of S given X and theta R that describe the eye movements S of a reader given a text X. Okay, so P of S given X theta R is a distribution over possible eye movement patterns S given the text X and the reader-specific parameter vector theta R. And if we assume a uniform prior over readers, so essentially we assume that all readers appear with equal frequency, then we can basically predict this most likely reader by just looking at the reader-specific model that has the highest likelihood on the test eye movement sequence that we've seen. Okay, so what we're going to do is we're going to determine the likelihood of these reader-specific models on the test eye movement patterns, and we're going to predict the reader whose reader-specific model has the highest likelihood on the test data. Okay, and now the kind of central question is how we define these generative models, P of S given X and theta R. And we are going to do that by formulating a kind of dynamic model of gaze control that successively generates these fixation positions and fixation durations that we see in the data given a particular text X. And to introduce some notation, for a given eye movement sequence, we will use S1 to ST to denote the fixation positions in the sequence, and we'll use D1 to DT to denote the fixation durations. So that's essentially the kind of data that we are getting out of an eye tracker. And we will define this P of S given X and theta by using a kind of Markovian sequential model that successively generates these fixation positions and fixation durations. Okay, so P of S given X and theta is going to be the probability of observing these S1 to ST and D1 to DT given the text X and the model parameters, and we assume that this is generated by a kind of Markovian model that successively generates the ST plus 1, DT plus 1 given the current values ST and DT. Okay. Okay, and how does this Markovian model look like? Well, basically, it's a kind of dynamic graphical model, and at every position in the sequence, we will first draw a so-called saccade type. The saccade type distinguishes 4 different types of possible gaze moves that we can execute as a reader. So we can refixate the current word, so the gaze can stay with the current word but move to a different position within the current word typically. Or we can move the gaze to the next word, which is actually the most frequent type of gaze move that we observe in typical data. Or we can perform a forward skip, which means that we skip 1 or more words and move like to the right of the text. Or we can perform a regression where we move back to an earlier position in the text. Okay? And we simply draw this saccade type as a multinomial variable from a multinomial distribution that gives the reader-specific probabilities for executing these different kind of gaze moves. And now after generating the saccade type, we draw the saccade amplitude, so basically the distance the gaze is moved in the text, from type-specific gamma distributions. So essentially for each of the different saccade types, there's one gamma distribution that describes the distribution over possible saccade amplitudes for this particular saccade type. And these gamma distributions are going to be truncated to account for the text content at the current fixation position. So for example, if I know that the saccade type is a refixation, then I know that the gaze has to fall within the scope of the current word that is currently fixated. And that, of course, constrains the saccade amplitude, and therefore we need to truncate these gamma distributions accordingly, depending on the actual text content. And after generating these saccade amplitudes, we draw fixation durations. So we draw a random variable that says how long this position is fixated, again from type-specific gamma distributions. So for each of the different saccade types, there's one gamma distribution that gives a distribution over the fixation duration. And in the end, we can just update the fixation position in the text based on the old fixation position and the saccade amplitude, so by how much the gaze was moved. Okay, and all the different parameters that we have in this kind of generative process that I explained here, so the multinomial distributions and these different kind of gamma distributions conditioned on the corresponding saccade types, all these parameters together kind of constitute the model parameters theta. And we are going to train reader-specific models. So for each of the readers, we are going to infer maximum a posteriori parameters of these models by using the eye movement observations of that particular reader that we've seen in the training data. Okay, so S1R to SNR, here are the eye movement observations of reader R seen on the training text X1 to XN. And as a prior distribution, so I said it's maximum posteriori parameters, so there's the obvious likelihoods like multinomial and gamma, and then as a prior distribution, we use a Dirichlet prior for the multinomial distribution and uninformative priors for the remaining distributions, so for these gamma distributions. And you can write that down as an optimization problem. It's going to look slightly non-standard because we are fitting these gamma distributions that are truncated differently at each data point. So that's kind of slightly complicating the optimization problem, but nevertheless you can write that down and you can solve it using kind of standard optimization methods. So we use some quasi-Newton optimizer here. Okay, and using that you can infer these reader-specific models by doing reader-specific maxima posteriori parameter estimates. Okay. So that was the statistical model of eye movement control that we use as a basis for inferring these different readers. Now I'm going to present some empirical results about how well this model actually works as a biometric model. So what kind of data do we have? Well, we have empirically studied how well the model distinguishes 20 different individual readers based on their eye movements during reading. And the data that we have are recorded eye movements of these 20 individuals on the so-called Potsdam sentence corpus. This is a kind of standard text corpus for eye movement research that contains 144 sentences overall. And the experimental setup is as follows. So we're going to randomly split the sentences into disjoint sets of training and test sentences. And then we're going to use the observed eye movements on the training sentences to estimate the reader-specific models that I talked about. And we're going to try to infer the most likely reader from the eye movements observed on all of the test sentences. So we're going to see the reader, for example, read 10 test sentences, and all the eye movements that we've seen on these 10 test sentences are going to be kind of our test sequence on which we evaluate the likelihood of the models. And this means that the more test sentences you have, the easier the problem actually gets, because the more information you see about that reader, and the easier it is to pick up differences in the distribution between the eye movement patterns. And finally, we measure multi-class identification accuracy as a function of n and m, so as a function of the number of training and test sentences that we've used in this setting. Okay, here's the first experimental results. So the plot shows accuracy as a function of the amount of available training data. So on the x-axis, we have the number of sentences from which we generate or on which we observe eye movements for fitting the models. And on the y-axis, we have identification accuracy as multi-class accuracy in this 20-class problem. And the red line here is our proposed statistical model. And that model reaches an accuracy of 98%, which is reasonably good for a 20-class problem, right? And then the other lines are different baselines. I don't want to really go into detail. The best performing baseline is an existing model for reader identification from eye movements that had been proposed by Holland and Komogortsev in 2012, and that is based on kind of aggregated features of an observed eye movement sequence. And this model reaches an accuracy of 91% in this setting, and random guessing is going to give us 5% because it's a balanced 20-class problem. In the plot here, we see the accuracy as a function of the number of test sentences. So essentially, the longer we can observe a reader at application time of the model, the more accurate the identification will become, because we're having like more and more information about the, we have seen more and more eye movement of this reader, and thereby we can infer the reader identity better and better. And here in the plot, the x-axis is the number of sentences that the reader has read at application time of the model. And the y-axis is again identification accuracy. And the red line is again the proposed statistical model. And we see that we start getting good identification accuracy at around, I would say, between 10 and 20 sentences read at test time. So reading 20 sentences, I think, takes about 30 seconds in this scenario and with the data that we have. So if we observe the reader for about 30 seconds, then we start getting good results. Okay, so here we see accuracy as a function of the number of individuals to be distinguished. So on the left-hand side, we have a simple binary problem where we just try to distinguish two readers. On the right-hand side, we have the 20-class problem that I already talked about. And essentially, we see that accuracy drops somewhat. Of course, it's harder if there's more readers that we need to distinguish. But if we extrapolate the curve, the model would probably still work well for like slightly larger numbers of readers. Okay, so a brief summary. We've studied individual differences in eye movements during reading for biometric applications. And we've basically introduced this statistical dynamical model of gaze control that successively generates these fixation positions and durations. And in the empirical study, we observed that eye movements as a biometric feature can identify 20 individuals with up to 98% accuracy. Yeah, thank you.
Time for questions.
Hi, nice talk. I was wondering if all your model parameters are different for different users, or do you take advantage of readers reading the same documents and training them, having some shared parameters?
Come again? So all parameters are...
All your model parameters, are they different for different readers? Or do you take advantage of having some shared parameters, especially when readers read the same documents?
So generally they are all different for different readers, and this doesn't really, we are not really using any information about like if they are shared documents. In our setup, actually all the readers read the same documents, but that's not necessary. I mean, the documents could also be different. We do some kind of back-off smoothing. If there's very little data for certain types of gaze moves, for example, there's like a joint model and we back off to that model if the frequency is like, if there's too little data points to estimate the gamma distribution is reliable, something like that. But that's more like a technical detail. In general, it's different models for all the readers.
I'm sorry, I missed the very beginning of the talk, so you may have said something about this before, but I'm wondering how disturbable the data that you got can be, say, if somebody is being tested under condition of stress, how much their patterns of reading might deviate from what you find in a more quiet experimental situation.
Yes, so that's definitely a valid concern. So the data that we have is, well, has been recorded with like students typically in a non-stress setting, I would say. So we did never actually address these things, if this might change if people are very tired or very stressed or whatever. I mean, if one really wants to seriously think about these biometric applications, one would have to do studies like that, obviously. So my personal guess would be that there's going to be some changes with stress level, for example, but the individual differences are so pronounced that I don't think this would completely like override the individual differences and make the model fail completely. But we haven't actually done the studies, so yeah, it's hard to tell at this point.
Well, actually, being this session quite interdisciplinary, I was wondering if there are studies that correlate the way, I mean, people move their eyes during the reading with their personality. Maybe the way they focus on words, they move from, they jump from words to words. Could be, I don't know if there is any. Otherwise, it would be interesting. I mean, to ask the readers to do the Big Five inventory test and to try to correlate somehow.
Yeah, that's definitely also an interesting direction for future work. We're also looking into a bit. So one can, of course, try to correlate eye movement patterns with other like characteristics of individuals. So, for example, it's well known that this correlates to some degree with age, for example, or also with education. I mean, obviously, if people are very well educated, they're going to be like have a lot of experience in reading simply, and this is going to influence the eye movement patterns, and also possibly other characteristics. Might be interesting to look into that. Yeah.
Very last comment, and it's a little bit off topic, but it would be also interesting maybe to correlate the way in a public long reading, the way people also move not only their eyes but their hands, you know.
Okay, yeah, that would probably give additional information that would be useful, I guess. Yeah, that's true.
And going behind the stereotypes that at least we have in Europe. I mean, actually, you move your hands more than Italians do. So, okay, thanks again. Let's thanks the speaker. So we'll move to the next talk.